above the level.
Oh, yes, right. Well, that's the good thing about being dirt poor.
That's it. You're a university, so we couldn't get any difference.
Wow. Well, I was really shocked when we got that.
So,
Yes.
Dr. Campins is
Yeah.
going to do the presentation in April with some of the results that they've gotten, some of the
Wow.
preliminary
Is he
results.
coming here or doing?
No, he's going to be doing it Zoom.
Cool. Excellent.
So, I'll send you guys a link.
Well, that's really clear, isn't it? That's,
Where are you going to do
that
this?
serves the purpose.
Sulphur Springs, Texas. Which wasn't a really first choice, but it was probably the closest point that we could get to without ways. And it didn't look like there was a lot of variation between the weather patterns from all the way up north down to south, and then you get down to South Texas where it's desert. So,
Weird.
and we didn't want to.
Maybe if you,
I got copies of that page in there. You already had the
Oh,
Astronomers.
okay.
yeah, I do.
Yeah.
What is it?
And
It's an atlas that, it's a page from an atlas that we have to share information from.
Right.
Oh, okay.
You know, like I say, everybody's gonna wait till last.
How come you're highlighting this part down here?
That's all right.
I was just curious why you have this.
I was amazed at how
I just picked it on the page.
last time.
To show what kind of information that's available.
Well, and I remember I was up in Hiawatha, unfortunately, where it was raining about 700 inches.
Yeah.
That was not fun.
So, I guess we'll go ahead and get started. Our feature speaker is Gary Hugg, but Parker asked me if he could just get a quick few minutes at the beginning to talk a little bit about the eclipse. And so, Parker Lesser, take it away.
Yeah, I'm going to be really brief here. Those of us that are going to be chasing the eclipse, I think, are prepared to have a full tank of gas and drive hundreds of miles above speed limits along dirt roads. If you're not familiar with it, there is an atlas that has the kind of information I just showed you along the entire path of the eclipse. And in 2017, I found it to be tremendously helpful as we started out in St. Joe and ended up in central Nebraska. And in the last 10 minutes, driving 60 miles an hour down a cornfield, almost literally, to get some clear sky. But this atlas shows all the dirt roads, everything, and it shows on the path of totality, depending on where you are, the number of minutes of totality that you'll have. And what I wanted to mention is that if you have a rough idea of where you will be, you could maybe send me an email or a text, and I would be happy to make a copy of a relevant page and send to you. You might find that helpful. The other thing that I wanted to very quickly share is a website, and eclipsophile.com, eclipsophile.com. I'll repeat that again. ECLIP, like eclipse, SOPHILE.com. And it has page after page after page of historic information on cloud coverage. And looking at that, things don't look as hopeful as what this isn't looking too hopeful either. There's going to be a lot of clouds, looking historically, and it has maps that give the likelihood of cloud coverage along the entire path. And let me just get to another slide here that for various cities along the way, again, it shows historic cloud coverage. You can read what the scales are when you go to the site. And let me go to one more to give you an idea of kind of information that they are providing. For various cities, again, it gives historic climate information. And as we get into closer to April, I know I'm going to be studying that very closely, and I wouldn't be surprised if others don't want to do the same. So, again, I just wanted to share that information with the hope that it could be helpful.
I don't know, the weather to me is gonna, I mean, look at our situation right now, we're gonna probably have the warmest month, so historical may not be too good. It's just gonna be a seat of the pants that day kind of thing.
Well, that's right, and I am fully prepared to do like I did last time, is at the last minute, decide within a state of where I'm going to be, and with the expectation that I might end up in a different state. But I can sleep in a car, I can throw a sleeping bag down the side of the road, I can do whatever's necessary.
I understand.
Anyway.
Parker? I will send some of those links that you mentioned. I'll put them in the newsletter coming up, so everybody will have access to that. So for our featured speaker tonight, we have an astronomer, an amateur astronomer from Topeka, from the Topeka group, NECAL, Gary Hug. He's also pretty famous amateur astronomer, actually. Several hundred main belt asteroids you've discovered or co-discovered. Tens of thousands of calculations on orbits for NEOs and asteroids, and the co-discoverer of a comet as well with Graham Bell. So we don't very often get famous people come in and give presentations. So Gary does a lot of work at Farpoint Observatory for the Topeka Club, and then he and Graham have their own observatory. I'm stuck.
Graham Bell?
Yes.
Yeah.
But what's the name of your observatory?
He has an observatory out at Maple Hill, hasn't had much success with it yet. And mine's at Scranton, Kansas, so I'm just south of Topeka.
Okay, so they've done, a lot of your observations have come from your
Yes,
observatory.
yeah,
actually.
more actually than from Farpoint, so.
Yeah.
We'll get into that.
So,
Well,
all right,
thank you.
well, Gary's going to talk to us a little bit about, for those that didn't know, there was a history with the 27-inch reflector up at KU when we had an observatory. The mirror went to NECAL, and they built a telescope around it at Farpoint. Gary came in and gave a presentation, I don't know, 5 years ago or 6 years ago maybe, about some of the updates that they had done to that telescope. And now they've done more, I guess, than just updates. And so he was going to give us a little bit of an idea of what's going on at Farpoint.
Hang with me just a minute. Get this thing up and running here. I think it is here. Okay, so we'll start there. Okay, this is an image many years ago, actually. Okay, now we gotta change stuff.
Yeah.
What you're going to see is an image many years ago that I took from my backyard, actually.
Okay. That's fine, yes.
Hello?
Nope.
There we go. Wrong one. That looks familiar. Let's start over here. Okay. There. Okay, we'll start with that one. There. Okay, so that image I took from my backyard using a device I built that tracks stars through long periods of time. This was like a 24 millimeter lens on a Canon, just normal, older now kind of camera. Nothing special about it. And it was about 13 minutes long. So it wasn't a short exposure here. I know they stack short exposures and really make some pretty interesting images, but this thing was 13 minutes long. So it was very long. And that happened about 6-7 years ago, maybe, in May. And it was early in the morning, so everything kind of settled down, and you got that morning sky. It always kind of helps a little bit, I think. Less atmospheric distortions and heat rise and that sort of thing. Anyway, that's what I did, and it has no reference to what I'm doing now. So this talk, it's just a pretty picture that I put up there. Okay, so thank you for all that praise. Probably not deserved, but you know, the thing of it is, if you're in anything, doing anything with any kind of degree for a long period of time, you're going to have some accomplishments. Yay. Okay. but it's been a long road, so you know it's as you guys know, it takes a while to build those up. Okay. Well, anyway, thank you very much for that intro. Let me go ahead and get started. There's a couple people in there that you might recognize. They were there when we had our grand opening, our dedication ceremony of a telescope that should have worked really well. It didn't, by the way. And unfortunately, Lindley Johnson, who is now the head of the Planetary Defense Office, was there also. So we got to demonstrate to him that we couldn't use that telescope very well. All right, the problems were this. In the bottom here, you've got the mirror. In the top, you've got a 10-inch flat secondary, okay? So light comes in past that great big secondary that's about 11 inches because you got to have a little cover around it. So, and then you go down to a 27-inch mirror. So you're taking out a pretty good percentage, even though it's an inside diameter versus outside diameter. I know that there's a big difference, but you're still taking out quite a bit. But here's the thing. And then it went down to a diagonal. I didn't bring my laser pointer. Diagonal right there. That went out to the side where the camera was. So in theory, this should have been nice because it's a short tube, doesn't pick up a lot of wind, and everything's kind of compact for this focal length. The focal length on the 27-inch mirror, by the way, is f/5.5. You figure that out. It's 148.5-inch focal length. Well, that's, you know, what, 12, 13, 12 and a half feet. And that's just the optics. And then you got another 5 or 6 feet here from the floor. So you're way up there in the eagle area. Which isn't that bad because you compound the scope. You shorten the tube up. That's okay. We did that. It just didn't work. Part of the problem was trying to collimate all these mirrors and get everything centered out, and each one of those sections baffled well enough that you don't pick up a lot of unwanted light. And we found that to be almost impossible to do. For our skill level probably isn't as high as some others, but we just never could get it to work out the way we theoretically thought it should. Okay? So, okay, all right, so now we got to change some things around. We can't live with this. We're going to have to see if we can work things out better. Okay, So, and this is the problem, and and then, you're welcome on these graphics, by the way. You don't have this kind of quality very often. Primary mirrors, 10-inch secondary, diagonal, camera. That's the way we start. Okay. All right. Now, the next transition, we decided, well, hey, why don't we do this? Why don't we just use the primary mirror, the secondary mirror, eliminate the diagonal, put the camera right in the middle of the scope? Yeah, we could do that. That'll work. So, and we thought this is really the way to go here. This is the best of both worlds. We still have a short tube. It's just that we don't have the camera sticking out over here. It's up here. We eliminated one mirror, one surface, one collimation problem, right? Okay, so that worked kind of good. Not as good as we had hoped. Okay. It was easier to collimate. Baffling was still problems. We couldn't restrict the unwanted light as much as we wanted to, because our camera was pointing up to the sky, for one thing, and even though we tried to limit it down in a baffling to limit that down to just that 10-inch secondary mirror, but just offset light. If you had a moon that was over there, a quarter moon that was over there, it's going to slam in. And it's very hard to take that out in this kind of design. So, and we still had a large percentage of the primary mirror blocked, of course. And we ran this way for a couple of years before deciding to change once more. Some idiot keeps wanting to change this thing. It's me. All right, so what we ended up with was doing the last modification here was we just went to a prime focus the entire length of that long drive down to the camera. Okay. Which, at this point, we can block the unwanted light a lot easier. There's no collimation issues because it's there and there. Pretty simple to collimate that. And we've worked that way for quite a number of years. Of course, with that, it's a long, long tube. 148 and a half inch outside the mirror. The mirror sets about 6 inches inside the end of the tube. And that tube sits up about 4 foot off the ground, where the declination, 5 foot off the ground, where the declination axis is. So now you've got this great big tube going up pretty high, and you guys know what I'm talking about here because you had the same problem when it was at KU, up in the observatory, the old observatory. It was monstrous big, any wind in it. We were able to work in about a 5 to 6 mile an hour wind or anything less than that. Okay. And you can see how long that tube is. That tube is as long as I am fat. Too long. It gets up in the air, it becomes a nice kite. All right, well, go back to that. Okay, this is a group of people that are on the NEO team now. David is our lead observer. I am kind of the backup observer. I'm the TI, or the, not TI, yeah, it might be TI. I'm the principal investigator of this process we got going. That David and me, Russ is our IT guy, and he's actually from Lawrence. He does a tremendous job of keeping us up and running. And then Doug is our K-State representative. He's a professor at K-State. And he's our kind of science advisor also. Okay. Okay, I don't know why this thing seems wanting to go backwards. Look at the thickness on this mirror. That's KU's mirror. It's 27-inch wide, but it's also 3.5 inches thick. Weighs about 200 pounds. See the bubbles here? This mirror was made before they really got a good idea of how to do the annealing process, which takes the bubbles out. Or else somebody wasn't up to date on how to do that at the time. But this is one of the, KU's mirror is one of the first mirrors that was, not the first mirror, but one of the first set of mirrors that were made with Pyrex. Okay, well, anyway, it's very heavy. It's about 200 pounds just for the glass. All right, but even then, with 148.5" focal length, if you get a good night, you can pick up something like this little guy right here, which is almost indistinguishable from all the noise. But if you see it, in motion, you can see it move in motion, okay? And fairly consistently. So that was Omaha, and this was taken at the time that it first hit the NEO confirmation page. This is about the second or third night from that. So our observations were included to make the determination that it was indeed an interstellar object. So that's what you can do if you've got everything working with you. Okay, so wind limited our dark sky time with long distance focus, and you can read through there. There was a need to go to a shorter focal length. And we thought, God, we had a shorter focal length, same size, shorter focal length, we could just use that, cut the mirror, or cut the telescope tube down. Fairly easy to do, relatively easy to do. So, and the 27-inch pit mirror that belonged to KU has a lot of historical value. It's Clyde Tombaugh worked on it for his thesis, was using that telescope as his thesis, or had something to do with it anyway. We didn't feel like we would be very comfortable even asking KU administration to change the focus on it, because that would be kind of destroying some of the historical value we thought. So now we're stuck, and I thought, well, okay, we just have to live with this until we can do something different. And just in one winter, I was kind of browsing through and found a place called the Mount Cuba Astronomical Foundation. And I say Cuba because I don't want to say Cuba, but I don't know what song it is. And I was real fortunate in the fact that it was wintertime, for one thing. It was just the first of the year, and they kind of had set their schedule to do donation request or foundation request, excuse me, sometime in April. And so I quizzed that and told him that we'd be interested in applying, and told him what we were up to and kind of what we were going to do. And he said, well, usually in the very early part of the year, in the spring like this, we don't have a lot of requests, so it would be a good time to get it in. You know, when you get something like that coming back, you go, okay, this is a green light here. So we went ahead and applied. I went ahead and applied for the group. We got it. $30,000 they were gonna send us so that we could get a new mirror made and then supply some materials, at least the money for materials, to rebuild the tube and get whatever else we needed. So, we thought, this is cool. So we got $30,000 coming in to do this, and we have no out of pocket, it's just a lot of labor, but you know, that's normal. So anyway, let's go on. Let's see. So here's the difference. Another one of my fantastic drawings there. You know, for somebody that's a machinist, I really don't draw very well. There's a 12-foot diameter tube, or the length of tube versus a 6.5 length, basically. That's what it comes down to. So you can see, we're really going to shrink that puppy up. Part of the thing that gives you the ability to do this and will still let you have decent field, or decent, what's the word I'm looking for, where we can find our objects well, drawing a blank, is the fact that today's cameras now have such small micron pixels. The camera that we now use has 3.76 micron pixels in it. So those are really tiny. Anyway, that gives you the resolution you need, even though you're cutting down the focal length.
Are you using a corrector lens?
I'm sorry.
Are you using a corrector lens?
Yes. Yes.
Field flattener of some kind?
Oh, yes. We've got a 3-inch, not Optec. What's that one called? Sure. Anyway, it's Televiews, 3-inch coma corrector. Yeah. And what that does is actually it gives you, instead of f3, which is what the mirror is, it gives you f3.18 or 3.48, something like that. Because the coma corrector is a 1.18 times magnification to it.
It's like a little Barlow lens.
Yeah, exactly. And that's how that works, I think. That way it keeps the things from the outside edge becoming distorted. I guess. I'm not an optician. All right, so this is a 22-inch diameter plate, and you notice these extension arms come out. There's going to be wheels on here that are going to pivot and hold the mirror, and this whole thing is going to go in and out based off of some stuff I'm going to put in here. Okay, this was all kind of designed. Every step was kind of on the fly. Okay, I didn't have a comprehensive diagram of what I was going to do. Eventually, I just started thinking, man, maybe if I do this, and then maybe add this, and so it really wasn't planned from the very beginning. Yeah, David.
Why did you have to redesign the mirror so?
Well,
Put nothing about.
if we get back to where that one picture was that showed the big mirror, first of all, it's thicker, and I've got to redesign it from that standpoint. The other thing is, though, when it was built, when the telescope itself was built in Utah, what they did was they put in push-pull pins on the very outside of that hex, on the back, the octagon basically was on the back of the tube, and they had push-pull pins there, and it was like 5/8 24 thread per inch or something like that. And those got really sticky and tough to move and just really didn't work very well. Okay, so I thought, we can redesign this so it works better. And I'll show you that in a minute. Okay, so here's a little bit of an idea, and I'm just not tall enough. Anyway, you see this little area right up in here? There's a handle on the back side and kind of a block on this side. Well, it's a threaded rod that goes through there. And that will allow us to easily move each of 3 axes so that you get the right tilt on that mirror so you can collimate it. It's much easier to do than having push-pull pins in 3 different spots going, you know, on the edge of the tube. So that was one thing I thought we really need to get rid of. All right, I'm going through kind of fast here, but this is interesting because I thought, you know, we've got this camera on the backside, and you really need to put some kind of baffle in front of it. So I just got a block of Delrin, the 5-inch round block of Delrin, and shaved it off using a lathe, and making my steps here. It's just plastic, but it has sharp edges, so you don't have that kind of diffraction roll. And then the 3-inch opening, which went to the coma grip. And then the camera sits back on the backside. And up here, these things were where the spider vanes go off of that surface and this surface, where it holds all that together in the front of the mirror, front of the tube, sorry. Okay, questions? I'm sure it's clear as mud at this point. All right, so that was kind of the easy part, actually. And here you can see where the triangles are. Now they don't have little cups on them. I put Delrin cups, and I cut out the center of those Delrin cups. They're about 1 inch diameter, and they're about a 1/2 inch thick, okay? And in the center of them, I've got a small bolt that locks down to here at each one of these 3 points on each one of the triangles. But I opened up the center of it, and you only have a small, like a 1/16 inch wide ring that actually touches the mirror. Now, why go so skimpy? Because that mirror needs to be able to move around a little bit. If you stick that mirror, if you got something sticking on the mirror, it's going to cause it to deflect. And an F3 mirror is very touchy, very touchy. So at one, it's a 2 inch outside, but it's like a 1 3/8 concavity, or that's what I'm looking for. I know I had it in my hand in a minute. Anyway, it's really deep in the interior. So you gotta really watch how you put this thing in and what you do to hold it. So these little Delrin cups that go in there only have a small amount of surface area clinging on that, so that when it sets down on those cups, it can shift around easily. Okay? You don't want to tie it up. It's got to have free movement. Okay? So this is all fun to build. And there's the outside of this is the big, like this area right here is the bottom of the telescope tube. And there you can see it kind of from a side view, and up in there is where those threaded rods are, and down here. Okay, so each one, and they're all independent. So this whole thing in this inside will shift around and give you the tilt you need to play with. There it is, kind of assembled with actually the new mirror before we took off the protective wraps. And you see these? This is an axis point right here, and that's curved to match the mirror. And these wheels are Delrin wheels, and there's 2 more of those. So now you've contained the mirror fairly tightly, but without any pressure. That's a tough one. You gotta have enough flexibility, enough adjustment to make sure that you are touching the outside mirror without putting any pressure on it. Its own weight will then cause some deflection, but not a lot. Not much. Okay, so, and then the tilt, is down in here. So you got the tilt adjustment, you got the sides that can give a little bit if they need to. There is kind of the finished product when you've got a much shorter tube. And now we've worked in 22, 23 mile an hour wind.
Yeah, wind's not a factor anymore.
So we've really cut down on the wind problem. So now we can use it even in our normal wind conditions at the observatory, which is, you know, like right off the foothills. So it gets pretty breezy. Okay. There's the camera we bought, and coincidentally, we got that funds from the Mount Cuba Astronautical Society to do the mirror, to reconstruct the telescope tube assembly, all that stuff. That was all covered with just, you know, labor on our part. Cool. But we had a STL 6303E camera that was not in great shape anymore. We needed a new camera. And we needed one that had small pixels and preferably was CMOS. Now with CMOS cameras, you really don't need to take a dark frame. Isn't that weird? You don't need it. Its background is stable over 1/10 of a second to 3/10 minutes. It's virtually the same. This is pretty incredible. You still need a flat field. You need I think what it's called, a zero.
Bias?
Yes, bias frame. Thank you. So you still need that, but you can get by without taking any dark frames. It's pretty amazing. Okay. So anyway, that came from the Planetary Society. Also had a grant available through the Shoemaker Neo grant that they run. And so I thought, well, what the heck, we'll just apply for that too. You know, and once we got the money from the Mount Cuba Foundation, we applied. I applied for the club from the Planetary Society and granted it again. We got a grant for about $10,000 to buy this camera, the one you saw. It's a full frame, 35 millimeter frame, and there again, doesn't need dark frames. It's amazing how much difference there is, and yet to get to the same value. And of course, we bin these up like 3 or 4 times, depending on the situation. So each one of these pixels are binned at like 3 by 3 or 4 by 4. And then we're still looking at 15 micron pixels. We're still in a pretty good range. Help me out here. We're at 1.16 arc seconds per pixel. It's a pretty decent resolution. Okay. All right. Anyway, and you can read through this if you want, and you know, I will mention our member who lives in Lawrence, Russ Valentine, is our IT miracle worker. Move over, Scotty, because this guy is good, and he has done a lot of work to get us to where we are. All right, so now I had an idea that maybe, because we've got this thing so that we can remote access it. Cool. That was one of the grants that we got from the Planetary Society to remote operate, be able to remote operate, set it all up to do that. And we can do this from home, so we can operate the telescope from home, roll the roof off, turn the lights on, off, you know, all that stuff. That's all done from home now. But we didn't have, and we thought that that with this mirror, the difference is with an F3, you really gotta be really tight on your collimation. So it can float a little bit, it can fluctuate a little bit, so we need to have some way of adjusting that. So if you've got a remote operation, you're gonna have some way to remote the collimation too. So those 3 spots, this is the shaft, the threaded rod that goes through, and those 3 spots, we rigged up, some mad scientist rigged up this assembly for each one of those 3, and these stepper motors are driven by remote access. So now we can collimate our telescope remotely. It's important to have something like that. This is a very ugly setup, but it works. I'm always going for something that works over fashion, as you can probably do. Okay, now, so I explained all that. Oh, yes, and see these? My personal thanks to Dr. Barbara Trarog, Dr. Bruce Trarog, and Stephen Shaw. I even got Stephen in there, for their extreme support and belief in us. Because, you know, why would you invest a whole lot of time and effort into some plunky amateur group? But they did, and thank you for that. And also, Colonel Lindley Johnson, who's the Planetary Defense Officer, for his assistance with NEO Fallout grant we received. That funding provided for to build the Tombaugh reflector to start with. Okay. I'd be glad to answer any questions you may have. This was kind of a quick tour through. It was over several years that all this took place, obviously, like about 10 or 20. I know I got a lot older while I was working on it. So,
A couple of us were talking earlier about, I don't remember even how it might have been 20 years ago. I don't know, when we took the club over to Farpoint.
Oh, yes.
What's that for you guys using for your nightly runs?
And we were just wondering if maybe we could set something like that
Oh,
up
sure.
again
Sure.
in the future. Maybe not one of the public observing nights, but
Yeah, just
we could
another,
just-
we have what we call members night too,
Right.
and maybe a members night would be a better one to go to.
Yeah.
We're now using,
Yeah, I can do that, sure,
Tycho Tracker.
that could be a problem.
You might talk about Tycho Tracker. Question over
Okay.
here was what software we're using.
Yeah, we were using Astrometrica for a long, long time, and it was kind of the standard for a lot of folks to use Astrometrica. A guy by the name of, can't think of his name. Anyways, from Austria. So when you paid the whole $25 he wanted, I had to up it a little bit because it was in euros. But he said, just send $25, I don't care. He's been doing this, Robert, Herbert, I think his last name, negative. Anyway, that's the software we used for many, many years to do the astrometry analysis.
We
Now-
talked about Astrometrica.
Yes.
Okay. And then we've upgraded and gone with Tycho Tracker.
Is that specialized to this type of operation?
So I don't know if many people in the room know about Tycho, Gary. With Astrometrica, it was more of a Where's Waldo hunt for asteroids moving across the field. And you can expand on this, I know, but with Tycho Tracker, you enter in all your observation images and it stacks it and it finds the object automatically given the parameters of speed and direction.
Oh, so it looks like moving objects in the plane.
It does.
Now-
And so it's quite impressive, but you have to have certain you have to have a pretty heavy-duty graphics card to handle. But I'm sorry, Gary, go right ahead.
No, it's all right. The graphics cards are important because it uses that like a CPU. It uses it like a hard drive.
Yeah, it uses it.
But yeah, it goes through the GNU and uses, yeah.
Yeah, how many sets of observations do you put in there? Is it a video frame?
It really kind of is determined on the speed and direction, well, speed and brightness of whatever we're looking for. If we've got something that's really bright, we don't need very many frames. You know, we're going to pick it up fairly quickly, so a dozen frames will work to pick something up that's like 19th magnitude. But if you're looking for something that's 21.7, you're going to have a lot more frames than that. And usually the ones that are 21.7 aren't moving, 30 arc seconds per minute. So what we run across on kind of an average is something that's about 20.5 to 21, somewhere in that range. It's kind of a rough area. That's a magnitude we go for. And we can go up to 22 in good conditions. But, if you got something that's running fairly fast and fairly bright, we don't take very many frames. A dozen, maybe 20 frames. And those are usually like 30 seconds long each.
Okay, does the software then look at a set of individual frames or a set of stacked frames?
Stacked frames. Astrometrica uses stacked frames. We'll stack maybe, if we got 21 frames, we'll stack seven times 3. So we'll do 3 sets of 7 stacks, 7 per stack, and then run their analysis that way. Tycho basically can do the same thing, except you could set Tycho's number of frames, or the number of sets of images that you want to stack into. So we could do, 30 frames in the first set, 30 frames in the second set, 30 frames in the third set, stack all those together and have just 3 points that we're looking at.
Does it do an average stacking or cumulative stacking?
It can go either way. You can have it. You can have it to add to average to. God, what was the other? You got like 5 different places that you can adjust, kind of the density of what you're going for. Normally, we just do averages. Just sometimes it's beneficial to not. The thing about Tycho Stacker or Tycho Tracker is this: if you put in 100 observations and they're 30 seconds each or a minute each, you can have that stack all of that. It will, and you tell it that I don't care what the speed is, I don't care what the direction is, find everything in the field. And it will do that if you got an hour or two to wait for it. Calculate out. And the better, the more intensity that you have for your GNU, the better, the faster you've got that, the more CUDAs that are involved, you'll have a fairly quick result. If you don't, if you have just kind of a standard low-grade graphics card, it will take a couple hours to do that. So, but it will find everything in the field within some reason. It's pretty interesting that you can do that, actually.
Well, once you have, let's say your discovery, do you then, you send that information off so others can
Sure.
Try to replicate and verify?
Right, yeah. You have to be very careful.
It may not be what you're asking. We send it into the Minor Planet Center,
Yeah,
which has the list of all the NEOs.
and they'll put that on the NEO-CP page, or NEO confirmation page, if it looks valid. If it doesn't look valid, they'll say, hey, no, we're not doing it. But if it looks valid, they'll put it on the NEO confirmation page, and then you wait, and hopefully within a few hours, somebody else will pick it up.
Very quick.
Yeah.
So you're talking about
Sometimes
you
it will.
discover?
Yeah.
Oh,
Okay, any other, yes,
Everything's working now, right?
yes.
What's the biggest flaw in your system right now?
It's a matter, right now, it's a matter of making sure that all these, I have, not only do I have 3 collimation points around the outside, which you can tilt the mirror, but I also have those 6 triangles with 3 points each, 18 point, and I've got a little tension bar underneath there that you can adjust to make sure that they're just hitting the back of the mirror, okay? So that you get them all, kind of make sure they're all level with the same amount of tension. It's kind of difficult to do without being there, because those are adjustable too, but I don't have those on motors. Nor will I probably put those on motors, because any amount of tension that you put that's more pressure than what it should have, you're going to be distorting the mirror. It's really tough to get all that exactly the same. Okay?
How faint can you go now?
Well, we've been able to go to 22 in the past.
How long exposure?
Oh, that's like probably 45 minutes. Yeah.
You might think about LSST is going to stop operating next year.
Yeah.
They're going to put out 100,000 signals a night in terms of
Yes.
telegrams.
Well.
So there's a lot of work out there that will need to be done.
Yeah, but they'll just
People
get
can't
it.
handle it, there's just so much.
But they'll
coming
just
out.
get it the next night. They'll pick it back up
Another
again.
100,000.
No, I understand what you're
There's
saying.
only telegrams every night.
Yes, right, right. No, I know. And in the interest of speed, you probably only take as much as you need to get to a certain depth, okay? And if you got something that's fast and bright, you pick it up real quick, you go on really fast. You get the process done and you can move on. So we've been able to do as many as a dozen a night, maybe a little few more, maybe up to 15 a night.
It depends on the scene, the sky conditions, and the magnitude of what you're going for. But on a really good night, I can turn in between 10 or 15 objects, and each object has 3 or 4 data point observations. So, and there are sometimes it takes me over an hour to try to find a 20.5 in Kansas skies. Kansas isn't very good on most nights, but the big helpful thing is wind is not a factor at all. With the
It used to
Tombaugh
be.
mirror, you had cloud cover, you got moonlight, and wind. So finding a night to work was crapshoot.
And we just have just about almost 1 degree field of view.
So what do? You have a list craft down of your targets ahead of time?
Our targets, I don't know if you can pull it up, Gary. The Minor Planet has a list of
I'm counting on this one, I haven't set that up.
NEOs that they are asking for data on.
I see, and then you can pick what's
And then you
best
go
placed.
to that list, find what you want. There are other lists out there, or Minor Planet also is looking for recovery of objects. Maybe they're traveling around the sun.
Oh my God,
Now
you're
we
in
think
order.
it's back close and we're looking for someone to find
I
it.
can't
Gary
remember.
recently
I haven't set
found
that up yet.
2 objects that were not seen for 9 and I believe 14 years, respectively. And that was, 2 or 3 months ago. So he got recognized for refinding those objects with the new Tombaugh mirror. And the new mirror is very sensitive, as Gary's trying to explain, compared to the Tombaugh. It tends to want to.
One thing we did was we baffled a little tighter this time. That picture with the Dell run with all the steps in it, leading in, and that really narrowed down considerably and baffled out a lot of unwanted light. So that helped quite a bit. And we do have pretty good, we only got 100% illumination in about 50% of the image. Okay, the rest of it starts to taper off to about 75 in the corners. Still works. Works okay.
Is temperature drop during the observation period a problem?
Not really. We actually have a focuser that is temperature corrected. So we don't use it that way because being in Kansas, the humidity is usually high enough that you don't have to worry about that. Temperature's not gonna drop fast, so you can kind of stay with it pretty easily. But we can tweak the focus a little bit as we go. That's all electronic too. So, yeah, it's not an issue, especially here. If you get out now, it may be an issue Tuesday night because it's supposed to be 75 for a high and 13 for a low. I'm guessing there'll be a pretty extreme temperature drop in that one, but it's probably not too windy anyway. No, we haven't noticed much problem with that. Yeah.
The time of night you make your observations,
Mhm.
are there sufficient observers willing to observe after midnight, or are you slanted much more toward early, before midnight?
I'm pretty crazy, so I'm 24/7. I mean, you know, that's all just, I'm just weird that way.
Yeah.
Yeah, but, you know, there's times when, you know, like David's gotta take off, he's got some appointment he's gotta go to in the morning, and he'll hand it off to me. I'll have mine going, and then I'll have to take on Farpoints also, and run the Tombaugh, so I got 2 telescopes up in the air, and both of them semi-remote. The remote part of mine is that I've got a cable that runs underground to my observatory that's 85 feet away. Farpoint is 25 miles away. So, but I can operate both of them at once. Some say kind of good. Once in a while I get a little hung up on trying to get everything done in this order and that order, but you know, but I can do it, and we get it run, and it works pretty well. We haven't had too much trouble with that. The only time we have a problem is if I have internet out, or if Farpoint has internet out. Okay, and right now we've got fairly good internet connection out at Farpoint, so we haven't had too much downtime for that.
There was a big AAT outage a few days
Yes.
ago.
Yeah, it didn't seem to affect us.
Good.
Yeah, we were okay this time. Okay, any other questions? Did I even answer your question?
Yeah.
Okay, because sometimes I ramble and I start
Long
off.
term, you may want to think about identifying the specific area to focus on, because you'll be flooded with options to look at every night.
Oh, yeah. Well, and obviously, you know, something up fairly high, something at 38 degrees. Something at 38 degrees latitude, or you know, is going to be where we want to be. So we want to minimize our error current we're going through, and so you know, anything that's up high, yeah, we'll go for that one. Yeah, I don't know what's going to happen. It's going to be interesting to see. And LST is how far away are they? They think from starting?
Another year?
I know they're doing some testing now.
Yeah.
And, yeah, well, we survived several kind of iterations. The thing we probably could do, though, is we've got photometric filters. There's plenty of photometry stuff to do and that sort of thing. We can convert over to doing that. But to answer your question of earlier, I now have, Farpoint's got 10,000, roughly 500 observations sent to the Minor Planet Center. I've got 17,000 observations from my observatory that I've sent to the Minor Planet Center. So together, we got 27,000, almost 28,000 observations that we've sent to the Minor Planet Center. That is a ton of work. Okay, but, you know, and we're still, I think, in the top 17 now of people sending in observations.
Will the
That's
Starlink
worthwhile.
satellites affect your work?
Oh, yeah, they do. Yeah, glad you brought that up, because they're a pain. They're a huge pain. And especially if you've got to shoot in that, well, and the Starlink satellites aren't so much this, but there's so many satellites up in that -5 to +5 degree range, you know, for geosynchronous satellites. There's a lot more geosynchronous satellites than there used to be. And then you add in all of Musk's stuff, thousands, tens of thousands of satellites. And the problem is that he's not going to be the only one. There's 2 other entities that want to put up 10, 20, 30,000 satellites. We're starting to show them in the fields. In every field we take almost, we get another satellite going through. And sometimes it wipes out your target. So you got to start picking through your images and taking out the ones with satellites in it in order to, you know, which is a lot more work. But, you know, that's the price we pay for technology, I guess. Okay. Yep. Questions? Are we done? Oh, yep.
Is this that first time here, or is there observation, is there a meeting? We're not sure what the journal world said there would be observation.
Yes, we're gonna be setting up telescopes here
Yeah.
shortly.
Yeah.
So it's just, we're new, and so I didn't know.
Yeah. No, I'm just the person that they put up in the front so that it distracts people from needing to go out to the observatory. But soon we'll be doing it.
No, that's fine.
Yeah.
I guess it's
All
not
right,
more
well,
than
thanks,
that.
Gary.
Sure.
That was very good.
And if you didn't see all of this one, it'll be presented at Farpoint Observatory's, or NECAL's, general meeting next month.